All right, let's go ahead and get started here. So we're just going to be jumping into our new lesson. Although actually I say that, but I need to do one thing really quickly. Hello. Upload the notes. Go into Teams here. All right, so we are going to be starting our next section here. Very, very kind of similar with what we have done up until this point, where we kind of introduced this basic framework, this like what is a function idea, and then from there expanded on that idea, looked at how do linear functions fit into this, how do quadratics fit in, how do polynomial functions, rational functions, all of that kind of fit into this framework. In that same spirit, we're going to be moving on to our next class of function. And again, just kind of seeing how does this fit in with everything that we've looked at up until now. That is going to be taking a look at the exponential function. Now, exponential functions are functions that can be written in the form f of x is equal to a times b to the power of x. So we're now, rather than looking at like x to various powers like we were with polynomials, now we're looking at some kind of number raised to the power of x. Couple of conditions, though, that we need to set on a and b. For instance, it is commonly said that a is not allowed to equal 0. This isn't like an issue with math or anything. We don't need to like worry about dividing by 0 or taking the square root of a negative if a is 0. It's just it makes our function fairly not interesting. 0 times b to the x is just going to be 0. And so we say, okay, yeah, that's cool and all, but we're going to restrict our view to kind of more interesting values of a. So saying that a is not equal to 0. Along a similar line, we'll say that b is not allowed to equal 1. If b is 1, 1 to the power of x is 1, regardless of what x is. And so we run into kind of that issue there again of like nothing wrong with having b be equal to 1. It's just not a particularly interesting function. You just get a constant function rather than exponential. Not a whole lot going on there. Similar vein, b is also not going to be allowed to be 0, although we'll kind of flesh that out. That one has a little bit more of a reason why, but like 0 to like 0 squared or the square root of 0, whatever. All of that is just going to be 0. So again, having 0 as a base also doesn't make sense. But there is a restriction on b that we have to place that is actually very, very, very important, as it deals with like the values of x that we can get away with plugging in, making sure that we are allowed to plug in as many values of x as possible. We need to make sure that b is greater than 0, or that b is a positive number. If we're thinking about like reasons that we might exclude values of x, what were our two primary reasons for excluding values of x? Why would we need to toss x's out of our domain? So one is we were worried about dividing by 0, and then the other one was taking square roots of negatives. So if our kind of condition here that we're saying is that b has to be positive, then which of those two are we primarily worrying about? We're kind of worrying about square roots of negatives here. All right. So for instance, if we were to write an equation, g of x equal to -2 to the power of x, notice in this case, the parentheses is very, very important, that -2, the negative is also being raised to the power of x. What would be a value of x where we would kind of inadvertently take the square root of a negative? Anyone know? How can I represent taking the square root as a power? Yeah, this is going to be if I tried plugging in 1/2 for x, I would get -2 to the power of 1/2, which we kind of translate to being the square root of -2. And so I run into trouble at the fractional values of x. So if I were to have a negative base, then I would only be allowed to plug in integer values. I could only plug in either positive or negative whole numbers. Negative numbers wouldn't really be an issue. For instance, if I looked at like g of -2 here, I'd get -2 to the power of -2. What does raising something to a negative power do? It takes the reciprocal, and so this would be like 1 over -2 squared, which is just 1 over 4. That's totally fine. But what's not totally fine is taking the square root of negatives, which we see at kind of these fractional values of x. That also kind of gives us a clue as to why b isn't allowed to be 0. 0 to the -1, we would run into problems where we are dividing by 0. 0 to the -2, so on. All right. So we sort that out. We exclude the negative values of b. Now, b is just a constant, though, so that's not even talking about what x is allowed to be. To that end, let's talk about the domain and the range for this particular function. If I follow these rules, a is not allowed to equal 0, b is not allowed to equal 1, b has to be greater than 0, do I ever have to worry about dividing by 0? No. Do I ever have to worry about taking the square root of negatives? No, that's why we have the rule here, right? B has to be greater than 0 so that I don't have to worry about taking the square roots of negatives. And so if I don't have to worry about those two things, what is my domain going to be? All real numbers, everything from -infinity up to +infinity. Thinking about the range of our function here. As far as the range is concerned, I want to focus first on this positive base raised to a power. All right, we can think of this as like a specific example. So if I have 2 raised to the power of x, what kind of values would I expect as I plug in values of x? Say again? Yeah, exactly. They're all going to be positive values. So thinking if I plugged in either big or small, really, exponents into this, we would expect to see some kind of positive value. And as x gets larger and larger in the positive direction, they would get larger. And then just remember, if I were to plug in, again, this like negative value, like -10,000, then really this is 1 over 2 to whatever that power is. And so we say that that's also going to be positive, right? Raising to a negative power doesn't change whether our number is positive or negative. It just takes the reciprocal. It puts it kind of in the denominator there. And so if b to the x is always going to be positive, what is the range of our function going to depend on? Yeah, it's going to depend on the value of a here. And so if a is positive, and we end up with a positive number times a positive number, then our range is going to be everything from 0 up to infinity. And If a is negative, we'll have a negative times a positive number. We'll have all of the negative values, everything from negative infinity up to 0. All right. That does a pretty good job of fleshing it out. We'll look at a couple of instances in which it's not quite this, but certainly for our parent function, this works fairly well as kind of giving us an idea of what's going on. Quick thing to note, we are getting really, really close to 0. We're not actually ever touching 0. So again, think about like plugging in negative 10,000 in for my x. I would get 1 over a really, 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 really big number. That's going to approach 0, but it's not ever going to actually equal 0. It just gets really, really close. And then in the other direction, 2 to a massive number is going to become really, really large. To that end, what do I get? What kind of object do I get if I'm plugging in large values of x and approaching either a value or a constant function as x gets really, really big? What kind of thing, what kind of feature of our graph do we get plugging in large values of x, seeing that we are like converging to a value or converging to a function? Yeah, we're going to get some kind of asymptote. In this case, vertical or horizontal, which one? Vertical is where our denominator is 0. Do we have any zeros, any denominators here that we need to worry about? No. So what kind of asymptote are we going to get? Horizontal. What is the value or what is the function that we are converging to? 0. And so we end up with a horizontal asymptote at y equals 0. Now, this is a little bit of a funky horizontal asymptote. It only works in one direction. So for instance, if we're thinking 2 to the power of x is our function, we only see this kind of convergence for large negative values of x. For large positive values of x, it's just going to get absurdly large. And we're not going to see any kind of like convergence. But for large negative values of x, we do kind of settle down in that way. All right, one more thing that I would like to address, at the very least, again, in terms of the parent function, we're going to see that shifts actually make this pretty difficult to capture. But in terms of this value of a and what this value of a represents, when I plug 0 into my function, so in other words, I'm looking at the y-intercept of my function. What happens when x is 0? What happens to b to the power of 0? It becomes 1. And so what's the only thing that I'm left with when I look at f of 0? I'm only looking at a. And so we might say that the y-intercept is the point 0, comma a. Again, barring any kind of transformations. So we'll see, looking at a couple examples, this is highly sensitive to shifts. This is both vertical and horizontal shifts. This is highly, highly sensitive to those. We're going to see that as well, yes. At the very least, for our parent function, it'll be y equals 0. But again, it'll be sensitive to some kinds of transformations, and we're going to look at those here in a second. Any other questions before we take a look at example 1 here? All right, so example 1 asks us to find the domain, the range, asymptotes, y-intercept. So basically what we just did for the parent function, but for specific values of a and b. So looking at a, this is fairly standard in this case, like A would be equal to 2, B would be equal to 3. Thinking about our domain, do we really ever have any reason to change our domain? No, our domain is always going to be negative infinity to infinity. Looking at the range here, what is our range going to be? 0 to infinity. How did you know that, Sumaran? A is greater than 0. A is positive. We're going to have a positive number times a positive number. That's great. And then also importantly, notice no vertical shifts. So the range, those outputs, those y values aren't being adjusted in any way, aren't being modulated in any way. And so it follows our parent function pretty much perfectly, pretty much to the T. All right, likewise, what is our horizontal asymptote going to look like? Y equals 0, fantastic. The 0 here and the 0 here are the same 0. So the fact that we are approaching 0 for our range, the fact that we are approaching the line y equals 0, those end up actually being the same. We're going to see that they track each other very closely. And then as far as our y-intercept is concerned, when x is equal to 0, what is going on with our y-intercept? It's going to be 2. 3 to the power of 0 is just 1. 1 times 2 is 2. So the y-intercept is the point 0, 2. So y-intercept is what happens when x is 0. And so plugging in 0 for x, we would see that 3 to the power of 0 is just 1. So that just like drops away. And we're just left with that value of a there, 2. Yep. All right, and we could certainly look at what that looks like. That's kind of spoilers for what's ahead. And it's pretty much exactly what you'd expect. Notice as x gets really, really large in the positive direction, it almost looks like we have a vertical asymptote. Like we get really big, really, really fast, but we're never going to find an x value that that we kind of reach where we can't go past it. Our function just gets really, really big, really, really fast. So we get this like vertical asymptote looking kind of thing, but if you were to scroll far enough up, you would find x values like continuing there. There's not like a line that we can't pass. It just gets very, very big, very, very quickly. Exponential functions. And likewise, kind of intercepting here at that value of a, and then at large negative values of x, kind of approaching 0, but again, never touching, just getting really, really close. All right. Taking a look at B here. In this case, we've got -4 times 2 to the power of x plus 1. Again, thinking of our domain. Any reason to exclude values? Nope, that's never going to be the case. Everything from negative infinity to infinity. What's going on with our range here? There are a couple of pieces that are going to factor into our range. Okay, so first thing to note is that a is less than 0. We're working with a negative value of a, which means what is kind of our starting range that we want to think of? Everything from negative infinity to 0. But then what am I doing to my outputs of this function? What kind of transformation do I have going on here? I'm adding 1 to every single output. And so rather than seeing a maximum of 0, what is my maximum going to be? 1, exactly. So this here is our range, really just coming from the fact that we are adding 1 to every single y value. Does adding 1 to every single y value change my x values? No, I'm not messing with my x values at all. And even if I were to kind of mess around with my x values, it wouldn't change the fact that it's all real numbers for x. All right. So likewise, thinking about the value that we are going to converge to, or to thinking about like the function that we are going to converge to, what is our horizontal asymptote going to be? So normally it would be y equals 0, the line y equals 0. But what do we have going on here? We've got the +1 that is affecting everything. And so what is the value that we're actually going to converge to? +1. Y is equal to 1. So again, normally it would be y equals 0, but we're changing that. We're adding 1. It's going to be y equals 1 instead. All right, and then one more, the y-intercept. Normally it would be what? 0, -4, but what are we doing to it? Adding 1, all of our y values increase by 1, and so it's going to be 0, -3. Okay, so A isn't always the y-intercept. The y-intercept is like a combination of A and K. Likewise, our horizontal asymptote isn't always 0. It's going to track our vertical shifts up and down. Same with our range. Our range's maximum and minimum isn't always 0. That's also going to track our vertical shift up and down. If it had been -7, then all of these 1s would have turned into -7s, and so on. And we can kind of see that here if we are looking at our function. Notice that without that +1, well, okay, so in this case, our value of A, our value of B are slightly different, and so it's not exactly the same function, but it's pretty close to just like a vertical reflection of our other function. Taking that positive versus taking that negative, flipping it upside down, multiplying by -1, hopefully a very predictable effect. And then what would we expect to happen when we add 1? Well, it should just shift everything up by 1, which is exactly what we see. So now notice that rather than converging to 0, the -4 times 2x piece does go to 0. But then what are we doing to that output? We are adding 1 to it, and so everything shifting up by 1. We don't see quite the same effect with our horizontal shift. For instance, noting for C, we do have a horizontal shift. But like, is the horizontal shift is adjusting the x values to the left or the right? Is that going to change my range? Am I changing my y values at all? No, that's not going to change my range. Is that going to affect my asymptote if it's not affecting my range? No. Oftentimes it would affect the domain, but in this case, our domain is just all real numbers. So do I need to worry about it affecting my domain? Not really. And so we really end up with something that is very similar. Now, kind of hilariously, what it does actually end up affecting is the y-intercept. Why is that? Well, when we plug 0 into x, what happens to 3 to the x plus 1? Does that b to the power term fully go away? Because of that plus 1 does not fully go away. All right, so thinking if I have like 3 times 3 to the 0 plus 1, this 3 to the 0 plus 1 does not fully go away. This is just going to be equal to 3 times 3, which is 9. And so what do we get from this? Well, really what we get is that the y-intercept is not really A. In fact, A, while being a piece of the y-intercept, is not a particularly prominent piece. Very sensitive to shifts in our in either direction. We have a lot of sensitivity to vertical shifts. We also have a lot of sensitivity to horizontal shifts. Only when we don't have any shifts is that value of A going to be the y-intercept. right, questions here with our setup? All right. So let's continue on then. Exponential functions, I would say, like, as far as when we're talking about the utility of functions and like properly understanding functions, polynomial functions are very, very important in the realm of math. I mean, the field of algebra is very literally the study of polynomials. And so even at a very high level, they are something that is very, very important. But it's not always super obvious how to extend our findings in polynomials to like modeling a real world situation. Quadratics, sure, a lot of kind of motion follows or tracks quadratics, and so like there's a lot of physics that you can do with those. But with just like random generic polynomials, it's like, what does the rational zero theorem do for us? What does finding these zeros actually kind of accomplish? And it's a little bit kind of difficult to fully articulate that beyond just like a pure math setting, that these objects are just important for math. Exponential functions are different. Exponential functions are really what we see when we're talking about like how real life scenarios are modeled. We'll look at some pretty cool questions kind of as we work that deal with these exponential equations, but thinking about like population dynamics, thinking about interest in your bank account, thinking about radioactive decay, thinking about if I put a hot knife into water to cool it down, how long that takes. All of this is very, very tied to our exponential functions. And we're also going to see the best number that exists ever, very, very inherently tied to exponential functions. So the plus side is that there's a lot of really great utility from being able to work with exponentials. The downside is that that means you're going to have a lot of word problems to kind of parse through. Okay, at its most basic, at its like absolute most basic, we are going to be talking about exponential growth and decay. I lump these as really the same thing. It's the same function. You'll have some books that like try to teach growth as its own thing and decay as its own thing, and I hate that. They are literally the exact same function. They are just a transformation of one another. In particular, the exponential growth model that we are going to use is that f of x is equal to a times, now instead of b, we're going to have 1 plus r to the power of x. So not really changing anything. We're just saying, okay, well, now b is going to be 1 plus r, where r is our percentage change. So for instance, if I had a population of bacteria, and that bacteria is increasing by 15%, the population is increasing by 15% every hour, and I want to know what's going on after 7 hours, that is the R that we're talking about, this 15% here. In particular, this isn't just something that you can say, oh, well, I'll take 15% of my initial population, and then that's how much I'm going to increase per hour. That 15% is going to change over time. The population is not staying constant, and so taking 15% of it will get you a different number each time you take 15% of it. So this is very specifically not a linear function. The faster or the larger our population is, the more and more and more it's going to grow because of that 15%. That's why we see the really explosive growth that we end up seeing. All right. So in this case, R is that change. Are we growing by 15%? Are we decreasing by 20%? Whatever. You could be positive, could be negative, again, depending on whether we're growing or decaying or growing or increasing. Why is that 1 there? What does that 1 do? Yeah, so if I'm increasing the population by 15%, is it enough to just multiply my starting population by 15%? Well, that'll certainly give you the amount of increase, but we're not looking for the amount of increase, we're looking for the population, and so we need to add that increase back into the original 100% of our population. So if R is the change, then that +1 is the initial 100%. Very good. And then kind of to that end, this value of A is going to be like our starting. It's like our starting amount. So if I'm starting with 100 individuals, then A in that case will be 100 and so on. 1 plus R kind of combines to be something very, very specific. A lot of people are really good at remembering that 1 when you are doing growth. And a lot of people are very, very bad at remembering it when you are doing decay. So for instance, if I tell you that something is decaying by 20%, we are losing 20% per hour, how much is left? 80% is left. 1 minus 20% is left. This quantity that we are raising a power to is not telling us how much is getting taken away. It's telling us what is left. So if I'm taking away 20%, 80% is left. If I'm adding 15%, then 115% is left. All right, and that'll all do kind of for now, at least somewhat superficially. We're relatively happy with where that leaves us. All right, so let's take a look at example 2 here. We are being asked to use our growth or decay model in order to find whatever information that we're being asked to find here. So for our first example, we are told that a radioactive substance is decaying at a rate of 2.4% each day. And we're trying to figure out how much of a 1,000 kilogram sample is going to be left after some kind of designated amount of time. So let's start with modeling this particular function. What is our value of A going to be? 1,000, so that initial amount there, starting out with 1,000. And then we start with that 1, right? Always starting at 100%. And then how much are we adjusting that 100% by? 0.024, 2.4%. And are we going to add on that 0.024, or are we going to subtract it away? Subtract, because we are decaying. Our amount is getting smaller, and so we will subtract 0.024. And then raising that to the power of x. What does x here represent? Time, but more specifically, the number of days is going to be very important to kind of note that in this case, this is number of days. You'd also think of it as like, I think this is kind of an interesting way to think about it, number of iterations. So how many times am I reducing by 2.4%? That's equivalent to how many days pass, right? But we'll see that kind of idea of number of iterations actually does become fairly helpful when we're looking at exponents that aren't just number of days. That is something that can be kind of nice. All right. And so what do I want to do? What do I need to do in order to figure out how much of my stuff is going to be left after 1 week? Raise this to the power of 7. So f of 7 is equal to 1,000 times 0.976 to the power of 7, which is equal to Said 843.62. Very good. All right, so that was not too bad. If I wanted to figure out what's going on after a year, what would I plug in? 365, so f of 365 is going to be, again, exact same thing, but I'm replacing that 7 with a 365. And what I get from that is 0.14 kilograms. Is that number ever going to hit 0? No. Mathematically, that's never going to hit 0. Now, in the real world, would we eventually reach a time where there are no more radioactive ions to decay? Sure. There are a discrete number of, of this particular isotope in this given sample. Eventually, we would reach a point where there just isn't another thing to split apart. But as it stands, kind of mathematically, this value would never actually hit 0. It would just keep getting smaller and smaller and smaller for increasingly large values of x. All right, questions with our radioactive, or not radioactive, but just exponential growth and decay models. Yeah, it's just the R would be negative instead of positive. Exactly. All right. I want us to take 5 or so minutes to try out B. So take a stab at B, trying to figure out what would a good estimate be for this fox population. And then just a thing to keep in mind, what are, not something that's rhetorical, or not rhetorical, but something for you to kind of answer on your own. What would a good kind of definition for X be? What is X going to represent? What are our units going to be? This is good. And then, yeah, just kind of a perfect. And is it possible for us to have that much of a box? No, so our best estimate was probably perfect. And like the decimal, because it's a decimal that 3 of a box. Yeah, that's perfect. That looks good. And then we just want to include the don't forget your power. Is our box population going to be getting bigger or smaller? Bigger. And then 13% will be 1. So that's more like no, what you have there is right. Yeah, perfect. Yes. Yes, this looks super good. Now, will we ever have that much of a fox? So for the purposes of that question, you'd probably average it there, but like, yeah. Very nice. Okay, looks really good. Looking at this, trying to figure out what is going on here. What is the formula that you guys came up with? To the x and then plugging in 15? It's 237 times 1.13 to the 15. Noticing in this case that it's a 13% increase per year. And so applying it as such, and we get that this would be around 1482 foxes. It's like 0.26, but you guys did a really good job of noticing we are talking about foxes, and it's a little bit gruesome to think about a fourth of a fox. And so we will instead round that to the nearest whole number. All right. Very good. Now, we are going to find that the two questions that we have just described, this was a very, very kind of blunted approximation. First of all, in terms of population dynamics, if we're talking about fox populations, it's a lot more complicated than just, oh, we're increasing exponentially. This is like making an assumption that like the foxes have an infinite number of resources and that 13% isn't going to change. Oftentimes what you would instead see is a much more complicated predator-prey model where, say, as a fox population gets a lot bigger, the prey population for that fox would get smaller. The prey population getting smaller means that the fox population would then get smaller. The fox population getting smaller would then mean that the prey population can get larger, which would then allow the fox population to get larger. And so you get this really, really kind of cool balancing act of what is going on kind of within the environment, and that can differ from like season to season. And so generally you end up with like these equilibrium points that you converge to, and so the population can look like a whole bunch of different things, and that is not something that we are going to be broaching. That is a differential equations question. So if you take math in college, that would be like after you do calculus. Kind of that next step would be, or one of the next steps would be like differential equations to kind of actually model what's going on there. But then the other thing to note is that even as a way to describe this fox population that's increasing at 13%, the thing that we basically just described is almost as if as soon as New Year's hits, that fox population is getting that 13% added on. And that's not very realistic. In fact, really what you'd see, particularly for things like this decay, fox populations might be a little bit more discrete, but in particular for the decay, it's not like it's watching a clock and then losing that 13 or that 2.4% all at once, all at one single time. It's spread out throughout the course of a day. You're losing a little bit of that 2.4% incrementally over the course of the day. And so the model that we have here, which is kind of this giant bucket loss all at once, losing all the stuff at once, is decent, but we're actually tomorrow going to come up with an even better way to describe what we are seeing here, which is going to be the difference between discrete growth or decay versus continuous growth or decay. Think of it as like a very optimized version of what we're about to see. Certainly not something that always applies, but in these particular examples, we wouldn't really expect this to be how the population actually grows. We'll look at that tomorrow. As far as kind of where we are here, we've got about 35-ish minutes left. Do we have any questions on what we've looked at with our exponential functions so far? All right. We got about 35 minutes left. In Pearson, there is a 3.1 through 3.3 classwork. So that will be due, I believe, set to be due next Monday, with my intent being that we'll have a quiz over kind of what we do this week on Tuesday. So we'll kind of take a look as we go. Other thing that I want to note, so I've just started kind of going through grading the tests. Our study guide completion for this particular test was maybe a little bit lackluster, not super great. Maybe I am projecting with how my other classes did, but I don't think I am. Yeah, study guide average was about a 57, which is pretty low, not super good. Now, it's about what the other classes have been as well, and their test averages have been better than what a 57 or a 60 on the study guide would kind of project. But we can either be working on that 3133 work, or the passwords for the late work for the study guide and the 2627 classwork posted to Schoology. Today is also the final day to get in the 2425 work if you are still messing up. All right. So taking the rest of this time, you guys are free to work on whatever you need to be working on during this time. Yes. Yeah. Yeah, so domain, is there anything changing or anything? Domain's just going to be infinity. All right, now notably, horizontal shift might change our domain, but in this case, because it's all real numbers, it doesn't actually change anything. Right? So often we would expect to see a change in our domain, but all real numbers is going to change. So is changing our x's, is sliding along the x's going to change our y's at all? No. So if our a value is positive 3, what would we expect the range to be? 0 to infinity. Very good. And that'll just be exactly what you would predict. Yeah, so domain and range don't change. If the range doesn't change, is the horizontal asymptote going to change? No. What about the y-intercept, though? What happens when we plug 0 into x here? Does that 3, does that base fully go away? It doesn't, and so the y-intercept is actually 9. It's a times b rather than just a. Yeah. So the only thing that changes there is the y-intercept, and it changes to mean a times b rather than b. Yeah. Of course. Sure. Yeah.
And then I finished the study guide.
Okay.
Does it do, like, is it late or is it?
No, you weren't. Yeah. Yes. So say again. So the range here is shifting to the left or the right going to affect our y values at all? Nope. And so what is our parent function range with a positive value of a? 0 to infinity, so that's what we would see. Yep. And likewise, the horizontal asymptote. Technically, the horizontal asymptote would slide to the left by 1, but it's a line, so you don't actually see it slide to the left. Yeah, it doesn't change the horizontal shift. Now, a slide to the left would change a vertical asymptote to the left. Right now? Yeah, we have time. That's the 2, 4, 2, 5?
Yeah, it was like.
Yeah. Let's see if I have any copies of that printed out.
I think I started it.
Let me take a look. I don't know that I held on to it. So I don't think we had really made much progress. Let me, yes, I can print out a copy real quick, and you should have enough time to work through that. And while we are here, let us do this.